So the speed of a mechanical wave depends on two things. First is the restoring force in the medium. Remember that when a particle is oscillating in simple harmonic motion, there is a restoring force that tries to bring that particle back to the equilibrium position whenever it's displaced. So the greater the restoring force that acts on each particle in a wave, the faster the wave will travel, because those particles are oscillating faster. And the speed also depends on the inertia of the medium. If the medium has a higher inertia, then it's harder to get the particles to oscillate with a certain speed, so the wave as a whole will travel slower. Now we're going to look at transverse waves on a string. So in a string, the restoring force is provided by the tension in the rope. So this is one section of a transverse wave, and so the particles at the crest are being pulled back to the equilibrium position by the tension in the rope on either side of it. So these ends of the rope are trying to pull these particles here back to the equilibrium position. And the inertia in the string is represented by the linear density, which is the mass of the string divided by the string's length. So the speed of a transverse wave on a string is the square root of the tension, the force, the restoring force, divided by the linear density, which again is the mass divided by the length. So if we have a string with greater tension, which means it's stretched really tight, the wave will travel faster. And if the string is more dense, it has more mass in a shorter length, then the wave will travel slower through that string. So now we're going to look at energy in these mechanical waves. So to get a wave started, to set the particles in their harmonic motion, we have to apply a force to the medium. And so since this medium starts moving, if we apply a force to it, then that means we did work on the medium. And so as the wave travels along, each part of the medium exerts a force and therefore does work on the part of the medium next to it. So in this way, the wave, as it travels along, and each part exerts work on the neighboring part, the wave can transport energy from one region to another. So we're going to look at the power, which is the work over time of a mechanical wave. So for a wave on a string, the power of the wave, the rate at which the energy is being transferred along the string, is varying in time at a single point. Sometimes, if we look at just one point, the power oscillates between 0 and the maximum power. So the average power is half of the maximum power and is given by this equation, which tells us that the average power, how much the rate at which power or energy is being transferred through this wave, is proportional to the square of the amplitude and the square of this frequency. So, for example, if the amplitude of the wave is doubled, then the average power will be quadrupled. Or if the frequency is halved, then the average power will be cut by 1/4. So this proportion, the proportion of the average power to the square of the amplitude and the square of the frequency, is true for any mechanical wave. So again, higher amplitude or higher frequency waves can transport more energy faster. So the power of a wave as it travels stays the same. But if a wave is traveling in 3 dimensions, then the power is going to be spread out over a larger area as it travels outwards. So we can define the intensity as the average power divided by the area. So for a wave traveling in 3 dimensions, that area would be the surface area of a sphere around the source where the wave started from. So if this point is the source of the wave and it's traveling out in 3 dimensions, obviously this is 2 dimensions, but imagine it's in 3 dimensions, and we draw a sphere around the source at any point we want, then the intensity of the wave at that point will be the average power divided by the surface area of the sphere. So as the wave keeps traveling outwards, the average power always stays the same, as long as it doesn't lose any energy. But this area that it's spread out over will increase. So the intensity decreases as a wave goes out from its source. And you can see it follows an inverse square law. The intensity is proportional to 1 over the square of the distance from the source. And so we can write that as a proportion between the intensities at 2 points on the wave. So if it's traveled a distance of 1 and the intensity at that point is I1, then I1 over I2 will be equal to the second distance, 2 squared, over 1 squared.